Hi, good morning, good afternoon, everyone. My name is Thirupathi Pattipaka, in short, Thirupathipaka. I'm director, data science and AI. I've been working for Novartis for last 5 years, and in my current role, I'm leading a team of data scientists, data engineers, solution architects to design various data engineering, data science pipelines and solutions to solve various drug development problems. Same time, my team is helping for internal efficiencies and external publication purpose with real world data. The data is coming from non-clinical trials like EMR, insurance claims, as well as registries and those kind of data sets. So today's my presentation is focusing on how can we use patient journey trajectories to predict disease progression and understanding subtypes using large language models. Before I begin, I would like to provide my personal disclosure. This presentation was prepared in my personal capacity, and the opinion expressed here are my own, and they do not reflect the views of Novartis or any other organization I'm affiliated with. So, why we need to do the this patient journey modeling, or understanding progression or prediction of the progression. So, the early prediction of the progression, understanding subtypes can help them various ways. Either it can help to the patients as well as caregivers with a chance to give a early intervention to the patients so that we can do the management of the disease very well, and allocation of the healthcare resource utilization, resources much better way, so that a patient will not deteriorate, and in early on right patient get the right treatment. But in generally, what happens in real world evidence studies is that the health events or data we will take at a single point of time or small number of time points in order to predict the disease progression, understanding the subtype, but and then same time ignoring the entire patient information that is available in trajectories. But if you look at the in general patient progression, that's not the data at one time. It is health events happening over the period of time, and each patient have a unique patient trajectories, and so that their uniqueness will drive to the progression and identifying the subtypes. So, with large language models and patient trajectories, it is possible to generate the new insights about the disease dynamics in real world, and especially focusing on the understanding subtypes, subgroups of patients based on the patient trajectories. We can understand the past progressors and slow progressors. At the same time, you can predict the patients at risk of progression at 6 months after progression, or 1 year, or you can even use the same methodology for the early disease to the latest disease also. And same time, you can build various kind of scalable applications, and so that you can apply to the multiple disease areas. And there are various applications also possible with this methodology. One of them is early prediction of the disease, which I already emphasized, that understanding the high risk patients to facilitate or treat the patients in early on, so that patient will not deteriorate, or patient will not go to advanced stage of the disease. And at the same time, same methodology, this patient trajectories plus large language models can help us to understand the patient readmissions, specifically hospital readmissions, and so that we can reduce the economic burden of the healthcare system. At the same time, there was an interesting paper also available what they have done is they predicted the patient's lives, and when this patient will die based on the various live events from the or sequences of the events from the patients. So, if we deep dive into what are the large language models are, large language models are subset of the deep learning models, and which is subset of the machine learning models. I've listed out four different types of the large language models here, but there are many large language models are available with the latest advancements of the GPT-4, or other tech companies. They released various kind of large language models. Okay, we understood that large language models are subset of it, and the patient journey modeling is very interesting, so that we can predict the progression, subtyping in a much better way. But the question is, how can we really input the patient journey into large language model representation? If you look at here, this the input of the large language models are like most of the transformers look like my dog is cute and he likes playing, for example. And then this one converts into various tokens, and the tokens are for example the starting one, and then my, and you can mask it, and then e is cute, and then separation between sentences and all. And then sentence embedding is the sentence A and sentence B, and then positional embedding is position 0, 1 to 10. So this is how the large language models take the input, and this is a more like a in general input representation of the large language models. And then if you look at the training and fine tuning process for the most of the large language models all look like this. So the first one is we mask certain like sentences, word embeddings in a sentence, and then after that we going to do the pre-training task. And you can see the left side is how the typical pipeline look like for the pre-training. And after that same after that we use the same kind of like LLMs for the fine tuning for the specific task. The specific task can be question and answer, or maybe sentiment analysis, or various downstream applications. So in the nutshell, what happens is that you will have a pre-training, just training the models, and after that fine tuning for the specific task. But if you look at the typical patient journey is very different. So you can see from the left side where the patient started as a maybe diagnosis, or maybe visiting the outpatient visit or inpatient visit or anything. So the representation what I showed here is for example hospital visit 1, visit 2, visit 3, and visit 4. And the patient before that patient might have a other outpatient visit, for example the showed in the dark blue color here, and then the light blue color represents the visit 1. And in a typical hospital visits, a patient will have a various kinds of events or data collected, different types of the data collected. That can be diagnosis. So here is R63, so diagnosis code, F50 is another one. So you can see the very sequence of the diagnosis codes that those are available at different visits. And at the same time, patients have a treatment, so though that is prescription. So 1032 is one type of the prescription, and then similarly you can see the various type of these prescriptions what patients get at the different visits. And same time patients get the procedures, and then you can also see the age and others. So you can if you look at the challenging part, what we have is LLMs will take the word side embedding, but our typical problem is our typical healthcare problem is very different. So but what we have done is we have taken the this patient journey or patient trajectories we fit into the LLMs in input as a like instead of words, we used the diagnosis codes, procedure codes, and other patients events as a word embeddings. Like you can see the its top, the data input for LLMs is look like that, visit 1 and visit 2. So you can see that each event as a word, a 06 and c 43, and separation and between the visit 1 and visit 2. And then after that you can see the visit 2 events also. Then in the pre-training, what we do is similar to the how we do the LLMs training, masking the particular word. Similarly, here we masked the diagnosis code or procedure codes, and then we did the pre-training. So it's very good. We understood from the previous ones is like how LLMs can take the patient journey events as an input. But what is this, like our project is about. So what we have done is we have taken the EHR data from the North America. So for each patient we create the patient journey. So the patient journey typically involves all kinds of events. I can show in the next slide. And as a patient journey or chronological, we think one patient is one sequence, and each diagnosis as a word, and each hospital visit as a sentence. What we have done. So then we have modified the one of the bet model. Like a bet is a model, and we created our own version of the bet models that called the expert, and pre-trained the model with non-disease specific cohort to predict the diagnosis codes, and fine-tune that task for the various kind of downstream applications, like the mortality prediction and progression prediction and risk subtyping. What we started up is we started up with 107 million patients, and then we have included only patients with hospital visits. Then we ended up with 37.7 million patients, and then we wanted to have a sequence of events. So that's why we included only patients with 5 hospital visits or more. And then after that we included the patients with only ICD-10 or ICD-9 as a primary visit. Then we ended up with a 5.5 million patients. So this is a final output. It look like. And if you look at the right side, all the information from the patients went into here. So for example, diagnosis information, what we talked, procedure and the labs and the age, BMI, smoking status, gender, and the segments, or like what kind of thing, and visits like visit 1, 2, 3, and all. And so everything, for the this what are the 5.5 million patients, we have created the uniform height of the all procedures, and the uniform of height of the labs, and other events as well. And first thing is we reshaped the entire feature matrix into a number of slots available, and wherever required we did the padding, and embedded this each token into 288 dimension vector, and sum the embeddings into column wise. And then this entire 5.4 million patients information we fed into the bet models. So we have compared the various tasks with compared with already existing traditional machine learning models, like a logistic regression, extreme gradient boost models, or like a bet models which are available. And there are like med bet, and expert is the model what we have. And then we also did the additional tuning also. If you look at the performance of the our model is clearly indicative of the death at 6 months and death in 12 months, and heart failure readmission. These are the 3 different tasks we have taken, and it's clearly performed better. So what is interesting also, especially death in 6 months and death in 12 months, those are the general task, and across all therapeutic area it performed very well. But hospital heart failure readmission is a specific task, and for that fine tuning was required. And looks like a fine tuning models are performed better than the without fine tuning models. So in healthcare, one of the important thing what we expect is the interpretability. So without interpretation of the models, trust within healthcare is less. So we have applied the expected gradients methodology for the interpreting the these results. One thing you can clearly see this. For example, the diagnosis is what you can see. The dark means higher importance, lighter means less important, and the diagnosis clearly the higher importance compared with the labs or procedures. And same time you can see the in this plot where x-axis is the number of visits, so visit 0, visit 1, in between visit 2 and visit 4 and all. And for the task of the 6 months mortality prediction after the first diagnosis, you can clearly see that the time goes past and diagnosis became the very very important. That means patients what kind of diagnosis patients has, and that is a driving factor for the mortality prediction. And then second important one is procedures, and then third most important information is labs. So in a way that patient's mortality we can understand whether patients will, I mean it, in general sense also it makes sense, right? Patients, what kind of disease patients has, it's a diagnosis information is important. And same time you can understand the procedures is what kind of treatments patients got, that is also drives the prediction of the 6 months mortality. And the labs also depends upon the type of the diagnosis or event, patients clearly get the different kind of labs. So the next one, what we have done is a clustering approach from the from the retraining the expert model. What we have done is in a way 5 different steps. First thing is retrain the pre-trained model on the predicting the cancer codes. Mainly we use the cancer codes for a year. And then after that we create the 2D embedding of the this entire expert model with using UMAP. And after that reduce this 288 vector embedding into the 10 embeddings with using UMAP again. And after that we applied the HPD scan unsupervised learning approach, and then we did the visualization of these clusters. This is a cluster representation what we have got from these results. And you can clearly see that patients with the lung cancer shown here, and the patients with the colorectal, like a colon rectum, they shown one side. And then also you can see the all the blood related cancer types including lymphoma, they are quite close. And breast cancer is a little bit higher, but compare with what we have seen earlier publications, the representations is very clearly visible. And you can clearly see the differentiation between the clusters. And you can also see the, for example, cluster 9, where is show the malignant neoplasm of the brain, and what kind of treatments labs patients got. And then cluster 1 is related to the multiple myeloma. What is also interesting is we can also take the one of the cluster, for example cluster 4, we have taken and then applied the clustering approaches again. And then we have seen the 3 different types of the patients also. So that is patients with different kind of things like a gray, blue and purple. And where you can see the purple is a clearly different from the other 2 cluster types. So with that, I would thank you to our group, like Adrian Cassidy and Chris Kaler, and at the same time to the Maurice as well as Orion, who has been worked with this project and generated the results. With that, I would stop here, and I'm happy to take any questions if you have. Thank you.